Questions about anything from before break? Well, I hope you had a good one. The week before break, I showed you the identity theorem, which is an important thing in the subject. Sometimes I call it the identity theorem. Some books call it the uniqueness theorem. I think our book calls it the uniqueness theorem. So be aware that those two things mean the same thing. Remember, it was a fact about the zeros of analytic functions on a domain. If the zeros piled up someplace in the domain, then the function had to be identically zero. So if the zero set has a limit point, or sometimes that's called an accumulation point, z naught, and it's important that that limit point be in omega. Then f is identically zero. So that means if the zeros pile up at a point, that can only happen when the thing's identically zero, because the zeros of analytic functions are isolated. That was the key to deducing that. Let's see, I guess I should show you an example of the zero set piling up at a boundary point. That's okay. So an example of, say, sine 1 over z on, I could take my omega to be the whole complex plane minus the origin. So let's see, sine of z is equal to 0 exactly at the multiples of pi. So sine w is equal to 0 if and only if w is a multiple of pi for some integer. Could be negative 2. Could be 0. So 1 over z is equal to n pi. Happens when z is equal to 1 over n pi. And we better not take n to be 0. So for n unequal to 0. So those zeros pile up at the origin. So if you think about, here's z equals 0, and then the zeros would be 1 over n pi, and they'd pile up. So these are 1 over n pi's. And they can be negative too, so they'd be the same over here. So they're clearly piling up, but that point is in the boundary of my domain. It's okay. Well, so, but sine of 1 over z is obviously not identically 0. And that's okay because the 0 is a boundary point. Of omega minus, of c minus the origin. Another example would be to take, or you could take my omega to be the disk of radius 1 about 1. Then you'd have a circle of radius 1 about 1, and then the bad point would be in the boundary again, this 0 point right here. And so here's 1 and 2. And then those zeros would pile up at the boundary point there. Questions about that example? And let's see, before break, the big application I showed you was that, here's an application. Let's suppose I have a domain that intersects, it could have holes, and let's say it intersects the real line on, could be a very small segment. So here's my omega. There's my omega, and let's suppose I have an analytic function on omega, f analytic on omega, and let's suppose that f of x equals e to the x on this little segment of the real line. On the red. Well, that red line has a limit point. In fact, every point in that red line is a limit point of the red line. And so there's a limit point that occurs in omega where I would, well, let's see, the function I would look at. The zero set f of z minus e to the z has a limit point. In omega. So it's identically zero. So there's only one way to extend the real exponential to a complex version. Last time I did it on the whole complex plane, but this theorem works in this context as well, on omega. Let's see. You might ask yourself next, yeah, question? F of z f of z minus e to the z would have zeros along that red dash, and so it would be identically zero, and therefore f of z has to be equal to e to the z. Let's see. You might ask next if there's an identity theorem for harmonic functions, and it's a little different. Let's see. Oh, and I use that argument to show that every trig identity you ever heard of holds for complex angles. Same arguments. So here's a corollary of the uniqueness theorem that's important. If I have an analytic function on a domain that vanishes on a little disk, if f is analytic on a domain omega, and f is identically zero on a little disk, so a little disk of radius epsilon about z naught contained in the domain, then it's identically zero on omega, because of course z naught is a limit point of that set. So that's kind of a heavy-handed application of that theorem, but it comes up pretty often and is useful. Interesting, this corollary has a similar version for harmonic functions. And this is as close to identity theorem for harmonic functions as we can get. So another corollary, the same is true for harmonic functions. So if U is harmonic on a domain omega, and U is identically 0 on a little disk, contained in omega, then U is identically 0 on the whole thing. You have to be a little bit sneaky to show this. So let's see. Remember when I was cooking up harmonic conjugates? There was an auxiliary function that was useful. So recall, if U is harmonic, then when you define a function, let's write it like this, capital F of x plus iy, I take du by dx in the real part, and I take minus du by dy in the imaginary part, is analytic. And that was a very simple application of the Cauchy-Riemann equations. Pops right out when you write them down. Well, if U is identically 0 on a little disk, then that analytic function, so let's see, this thing is analytic on, it's analytic on omega. Okay. And so this hypothesis would say, note that F would be identically 0 on that little disk where the U is identically 0. So F would be identically 0 on omega. How am I going to see that U is identically 0 from that? Let's see, so F is identically 0. Got to think about what the heck that would mean. That means that du dx and du dy are identically 0 on a domain. That's important that this thing is a domain. In other words, the gradient is 0. And so there was a result we had. I got it by zigzagging along curves and using connectivity, that if the gradient of U is identically 0 on a domain, then U is constant. So I don't know it's 0 yet, but I know it's constant. How do I know it's 0 now? Anybody? I'd assume that U is 0 on the little disk. So if it's constant, it would be constant on that disk, too. So the constant has to be 0. So since U of z naught is 0, that constant must be 0. So that's how you do it. Questions about anything? So it's natural, once you see this, kind of feels like harmonic functions are going to be very much like analytic functions. Question: is there an identity theorem for harmonic functions? Can the zeros of harmonic functions pile up? So that's kind of what that, can the zeros of harmonic functions pile up in a domain Well, you could think about that and try to prove a theorem like that, and you'd get stuck because it wouldn't work. Because there's very simple examples that show, for example, we know that u of xy equal the real part of an analytic function, namely x plus iy, is harmonic. And you can just check the Laplacian. But its zero set is the real line. What is it? It's the imaginary axis. The zero set is, let's see, I'll have the complex plane. X is 0 along the real line. So, so the zero set is that red, it's the imaginary axis, which has gobs of limit points. And so there's no theorem that says they can't, if the zeros pile up, then it has to be identically zero. And it turns out to be pretty interesting to figure out what the zero sets of harmonic functions look like. They always look like curves, and those curves can only cross at very specific angles, namely 2 pi divided by n for some n. So they're in fact, they can't have any ice. Well, that's a question. An interesting question. In fact, was this a homework question in here about the zeros being isolated? I didn't do it. No, that was my other class. It's a typical question we'll think about here, too. So I'll let you think about it for a while. Here's another question. Now that we've seen this zero set looks like a curve, another question might be, can a zero of a harmonic function be isolated? All by itself. I'll let you think about that before I tell you the answer. The answer is no. There can't be an isolated zero. And the hint for how you would think about it is the averaging property. I'll let you think about it before I show you that argument about how that's going to work. If it had an isolated zero, then you'd do the averaging property on a little circle, and it's not zero on the little circle. And in fact, since that's the only zero away from that circle, on the circle it would have to be either always positive or always negative. And so the average would be something strictly positive or something negative. So you got to think about it a little bit to come to that conclusion, but I'll show you how that works sometime soon. But I want you to think about it a little bit before I do. Questions? Yeah.
Curious, for the thing about the imaginary axis, so is there a limit point or? I don't know.
Every point on the imaginary axis is a limit point of the complex plane. So this is, let's take our omega here to be, it's harmonic on the whole omega equals c. And every point of the imaginary axis is a limit point of itself. And those limit points are in C. So if there was a theorem, that would mean that the function x is identically 0. So there is not, which it isn't. So there's no theorem. I might have some extra time today to do this. Why don't I show you this thing? So we know harmonic functions satisfy the averaging property. Do we? Okay. So let's see why. Let's suppose that suppose z naught is the only 0. Of harmonic function u in a little disk of radius epsilon about z naught. So it's isolated. It's all by itself. Okay, so let's think. So I've got a little disk of radius epsilon here about z naught. And what I claim is that U has to be either always positive or always negative in that punctured disk. So my claim, U is either always positive greater than 0, or always less than 0 in when I puncture the disk. So that would be the disk of radius z naught, epsilon about z naught, minus the center spot. Why would that be the case? So I guess the natural thing is if there was a spot where it was positive and another spot where it was negative, why would that just... Yeah, you're thinking of exactly the right thing, the intermediate value theorem from freshman calculus. The thing is, the intermediate value theorem was for functions along the x-axis. So we got to think about how we might get a one-dimensional thing to think about. So let's suppose that got a point right here where u is positive, and another point over here someplace where u is negative. I could draw the segment joining those two, but it might go through z naught. But I could, if that segment went through z naught, I could make it like bend around it. And so in fact, this is a connected set, so I know that I could take a curve that starts at this one here and goes around to that one. So there'd be a curve gamma, and I'd parameterize it by z of t, as t ranges from something to something. And then the aha moment is I could apply the intermediate value theorem from freshman calculus to u of z of t. It would be on the interval AB. Okay, that function would start out positive and it would end negative. And so at some point in between, there would have to be a place where it would be 0. So I get a t naught. I'll call it a tau naught. It can't be the endpoint where u of z of tau naught would be 0. And that violates, that would be the z of tau naught right there, would be a 0. And that violates the fact that z naught is the only 0. So that's a contradiction. Z naught is the only 0. In the disk. Okay, so now if I was going to do the average, it's either positive or negative. So now the averaging property would show me that u at the center would be 1 over 2 pi the average of u of z naught plus r e to the I t dt for radii that are between 0 and epsilon. Okay, and so this thing is either always positive or always negative, and so that would give me a strictly negative or positive value for z naught. So u of z naught is either greater than 0 or less than 0. And that's a contradiction. We assumed it was an isolated 0. So I like that argument. It's simple, and it just uses the averaging property. So harmonic functions are pretty different than analytic functions when it comes to zeros. We know analytic functions, zeros are isolated. And for harmonic functions, they can't be isolated. So they're way different. Well, I'm preparing for next time to show you Laurent expansions, which means I'm going to have a Cauchy integral formula on an annulus. But before I get a Cauchy integral formula, I need a Cauchy theorem. So the next topic is a Cauchy theorem for an annulus. Let me draw a picture of what it's going to look like. We'll have, let's see, I'm going to have an annulus. I'll have a center, call it Z naught. I'll have an inner radius here and an outer radius. And I'm going to have a function that's analytic on this annulus. So f is analytic on that open annulus. So I guess one way to write an annulus would be to say, call it A of, it's centered at Z naught, and the radii goes from little r to capital R. So that would be equal to the z such that little r is less than z minus z naught is less than capital R. That's an open annulus. Okay, well, we know the Cauchy theorem for circles on a disk. And so this is going to involve circles in the beginning. Let me take... I like my circles to go counterclockwise. Okay, so that the inner circle is going to have radius, let's call it rho 1. And the outer circle is going to have radius rho 2. It's getting kind of busy. Anyway, the Cauchy theorem says that the integral along the outer one, that's rho 2, about z2, minus the integral, the counterclockwise integral around the inner one, f dz, is equal to 0. Okay, so here I'm going to take r less than rho 1 less than rho 2 less than capital R. And these two things are counterclockwise circles. Okay, and I'll explain why that's a Cauchy theorem in a second. Questions about the statement of it? Well, the proof is going to be a picture proof, and since it's an annulus, I can get pretty concrete about it. So let's see, I'll have this circle and the inner circle centered at z naught. And let's see, if I go counterclockwise on this one, and then, so this would be going the other way, this outer one would be c rho 2 of z naught, and this inner one going clockwise would be, let's see, I want to make it clockwise. That would be minus c rho 1 z naught. And let's see, I'm going to do the Cauchy theorem on a simply connected region. And so I'm going to do that, I'm going to take a cut. I'll take cuts here and here. Okay, let's see if I do a cut. I'll go this way when I go around the top, and I'll go this way when I go around the bottom. So that top one gives me a counterclockwise curve, and I have I have a simply connected region where the thing is analytic. So here on the top, I would take my region where it's analytic to be something like this. So this is a domain. F is analytic on this simply connected region here. There's no holes in that orange thing. And I have a closed curve in a simply connected domain. And so the integral around the top half would be 0. Okay, so let me, this is going to be, let me copy this mess. Okay, so before so the integral around gamma sub top of f dz is equal to 0. And now when I do the same thing for the bottom half, I need to pick a different domain. So let's see. Let's see here. Yeah, so when I do the bottom half, what should I do? I shouldn't take this thing. I should take this thing. I'll take my my domain to be this one now. This is a domain for the bottom half. Where I would have f to be analytic. And so I get the integral around the bottom half of that curve. Let's see, on my blue, the blue stuff is going like that and like this. So that's a counterclockwise curve inside that domain too. And so we get integral around gamma sub bottom of f dz equals 0, 2. And when you add them up, the cuts cancel. And so you're left with the integral around the blue stuff. So integral around gamma top plus the integral around gamma bottom of f dz, let's see, that's why I would have the integral around the row 2, and then I would have the integral going clockwise, which is minus row 1. And that thing is equal to minus the integral around C row 1. And so that's the result. So this is a big fat 0. 0 plus 0. So that's the demonstration. Well, we've seen as soon as you have a Cauchy theorem, you get a Cauchy integral formula. Question? Yeah.
Does it not matter the fact that both integrals are done on two different domains?
It's the kind of trick we've used before. When you add them together and notice that the cuts cancel, you're just using Cauchy theorem on each of the halves.
Oh, wait,
Yeah, and so when the cuts cancel, they just don't come into the picture in the end. They're temporary. Well, this gets me in a good position for next time when I'm going to demonstrate Laurent expansions. So from a Cauchy theorem, you get a Cauchy integral formula. For an annulus. So I have to draw that same picture. So F would be analytic on a bigger set. I don't want to I guess I should emphasize that. F needs to be analytic on a bigger annulus than the blue stuff. And let's see, I'm going to take, I like my circles to go counterclockwise. So they're both going to go counterclockwise. And now I'm going to pick a point A here. A has to be in the annulus between the blue curves. And then we have the same hypothesis as before about being analytic on a bigger, same hype as before. But this time we'll have an A in the annulus from, let's see, centered at Z0 between row 1 and row 2. Z0's in the middle. Well, then guess what? The Cauchy integral formula would say that f at A is equal to 1 over 2 pi I, and I need the integral, same integrals I had before. And now it's the same old Cauchy integral thing here, f of z over z minus A. So the value inside the annulus is completely determined by the value of the function on those circles. Oh, let's see. Let me show you the proof. It's going to be a snap. So I'm going to do the same thing I did before. This time maybe I could have made the A along the horizontal direction. So just to emphasize that I maybe would have to avoid the horizontal, I'll take different cuts this time. I'll take cuts like this. Let's see, my circles are going like that. So if I take cuts like this, let's see, got to go that way, and when I go the other on the bottom half, I would go this way. And notice since those are different directions, when you add those integrals up, they would cancel. And this time I would integrate both those things, but I'd have a Cauchy theorem on this part. Did I do them the wrong way? No, what the heck? I'm sorry. I made this. Something's weird. I need to make I have a minus that other one, which means that's the integral along minus that. That's the clockwise version. Okay, so let's see. Now when I make the clockwise version. Right, so that's minus that curve, and that's why the integral is a minus sign there. Okay, so when I add those two halves up again, I get the Cauchy theorem on this side. So use the Cauchy theorem on this half. Since the function inside the integral is analytic there. So f of z over z minus a is analytic inside and on. On the curve. And on this side, I've used the Cauchy integral formula, which we know for on a simple closed curve on a simply connected domain. So we use the regular Cauchy integral formula. On this half. And you add them up and you get the Cauchy integral formula. That's all there is to that. Well, that's interesting. Because when I got the Cauchy integral formula on a disk, that's how I could see that analytic functions were given by power series. And so our next topic of that we're going to study are isolated singularities. Of analytic functions. So Z naught is an isolated singularity of F if there's some little radius, if F is analytic on a little punctured thing on a disk of radius something about Z naught minus Z naught. Okay, it could do something bad at Z naught. It could blow up, like 1 over Z minus Z naught would blow up. And we'll see there's other possible behaviors. In fact, there's only 3 possible behaviors, and we're going to deduce that soon. Okay. Let's see. Let me give you some examples. Let's go through the basic examples. I guess an easy example, 1 over Z minus Z naught blows up at Z naught. And so does 1 over Z minus Z naught cubed. So does there's a name for that kind of behavior. That's called a pole. So example A here, this f of z has a pole. If it blows up like that. That's one typical behavior. When you think about the difference quotient of an analytic function, it's not defined at the spot. So think, let's think f of z minus f of z naught over z minus z naught. That's the difference quotient for when we were doing the derivative of an analytic function. It's not defined at z naught. But if the thing is analytic, remember its derivative is analytic too. So let's think when f is analytic. F analytic near z naught implies f prime is analytic near z naught. Let's see, I don't. I don't want to think about that just yet. So this is here's my motivation for what I'm about to do.